Humans have been exploring Mars with robotic spacecraft since the 1960s. We have learned that liquid water once existed on the surface, and that the planet had a warm, wet environment that could have supported life as we know it. Was Mars warm and wet for long periods during which life could have arisen, or mostly cold and dry with only brief intervals that could have supported life? What was its early atmosphere like? Can we find direct evidence of past life there, such as fossilized microbes or ancient chemical signatures that resemble life as we know it? These answers can be found in Mars' rocks and soil, which lock in atmospheric gases, preserve signs of past life, and carry clues revealing the environment in which they formed. Despite impressive advances in miniaturizing science instruments for space missions, certain questions can only be answered by tools that are too large, heavy, and power-hungry to fly on spacecraft. Fortunately, there's a way around this limitation. Rather than bringing our tools to Mars, we can bring Mars samples back to Earth. To date, humans have only returned samples to Earth from 4 other bodies in the solar system: the Moon, asteroids Itokawa and Ryugu, and the tailings of Comet Wild 2. Samples from asteroid Bennu are scheduled to arrive back on Earth in 2023. Mars is a far more challenging destination than any of the above examples. It is farther away, with a thin atmosphere that complicates landings and a gravity field almost 40% as strong as Earth's, which makes it harder to blast back off the surface. Only in the past decade have Mars landing technologies improved enough for us to be confident that we can land in the same spot multiple times, an ability needed for multi-spacecraft sample return missions. NASA's Perseverance rover, which launched to Mars in July 2020 and arrived in February 2021, is the first step of sample return. It's exploring Jezero crater, the site of an ancient lake and river delta. There, the rover is using its onboard drill to collect and seal samples from rocks that formed in Mars' warm, wet past. The rover is leaving those tubes on the surface for a future mission to return to Earth. Getting those samples back to Earth could take 2 additional missions, possibly launching in 2027 and 2028, for which NASA and the European Space Agency will team up to share expertise and cost. The agencies had originally planned to send a fetch rover and its associated lander to Mars. But in July 2022, NASA announced it no longer intended to use either. Instead, the agencies are planning to use Perseverance and 2 Ingenuity-inspired helicopters to fetch samples. With its architecture solidified during this conceptual design phase, the program was expected to move into its preliminary design phase this October. In this phase, which is expected to last about 12 months, the program will complete technology development and create engineering prototypes of the major mission components. ESA is continuing at full speed the development of both the Earth Return Orbiter that will make the historic round trip from Earth to Mars and back again. and the sample transfer arm that will robotically place the sample tubes aboard the orbiting sample container before its launch from the surface of the red planet. The first step in the Mars sample return campaign is already in progress. The Perseverance rover has collected 11 scientifically compelling rock core samples and 1 atmospheric sample. Bringing Mars samples to Earth would allow scientists across the world to examine the specimens using sophisticated instruments too large and too complex to send to Mars, and would enable future generations to study them. Curating the samples on Earth would also allow the science community to test new theories and models as they are developed, much as the Apollo samples returned from the Moon have done for decades. This strategic NASA and the ESA partnership will fulfill a solar system exploration goal, a high priority since the 1970s.